Welcome back to the course on architectural design of ICs. So, we are seeing the different adder architecture. So, we have seen ripple carry adder, we have seen carry skip adder. Okay. So, after that we have seen that a carry skip adder, if we just make it a group for if the number of n is large. So, at that time if we make it a group and then using that group, if we just use that means the carry skip adder for each of this group, then we can get the benefit or that delay has been reduced by the factor of k. So, that means whatever the length of that group we have, the corresponding bit position of each of this group we have considered, the delay has been reduced by the factor of that. So, after that again what we have seen that instead of that, as this in the LSB group, if we produce one that carry, so that has to be passed through the, that means LSB, and unless and until we are reaching to the MSB, that carry will not be assimilated. So, that is why what we see as it has to that means traverse towards the, that means from LSB to the MSB. So, that is why what another technique we have used, that is variable that grouping we have done. So, instead of keeping that k fixed to each of this group, we have chose dynamically, that means changed value, which is that for each of this group for LSB and LSB, keeping the LSB side and MSB side, the group that means the word length for the group at the lower values, whereas the middle portion where I will group the middle portion of this corresponding bit position. So, at that time I will choose more on that, that means the word length will be more on that. And if I do that, at that time what happens, I am getting the corresponding this delay reduced by a factor of square root of n, whereas instead of in the earlier case just variable that block adder, if I use, at that time I can get the, that means delay variation, that is n by k. So, that means I can reduce the delay by more if we choose this multi-level variable block adder operation or architecture. So, again today we will see that means another architecture which is carry look ahead adder. So, in the carry look ahead adder we have already, that means seen this, that based on this the input bit, the carry is generated and the carry is propagated. So, this is that means this is the logic A XOR B, that is the logic for carry propagation, and A XOR B, that is the logic for carry generation. So, using one marks easily I can just do the, that means I can skip this, that means at what bit position, whenever this propagated value of this is 0, at that time it will select any values of A or B, and whenever this value is 1, so at that time it will select the corresponding carry in bit after considering the operation table of full adder cell that we have seen. Okay. So, what we have done, firstly what we have done, we should examine a realization of 1 bit adder which represent a basic building block for all the more elaborated addition operation. An operation of a full adder is defined by the Boolean equation for the sum and carry signal shown in this particular slide, which is Ai, Bi and Ci are the inputs of the ith full adder stage, and whereas this Si and Ci plus 1 are the sum and carry output from ith stage respectively. From the above equation, it is clear that the realization of sum function require 2 XOR logic gates, as sum function is what, A XOR B XOR Ci. Okay. So, that means 2 input XOR gate I need 2 level, 2 input XOR gate, that means I need 2 levels. So, the expression for carry function could be rewritten using the carry propagate Pi and carry generate Gi terms. If carry propagate is 1 and the carry out of the stage will be equal to carry signal into the stage Ci plus 1. So, that means that is we have generated, and so what happens is actually if we take this example. So, if we take okay, so this is the carry which is generated at the very first level. Okay. So, what is the carry what I written, that is carry is a b plus a XOR b into c in. So, for the first level okay, that means first level means after the LSB. So, where I need A1 and B1 is the input. So, A1 B1 plus A1 plus B1, sorry, this is not plus, this is XOR. Okay. So, A1 XOR B1 into C0. So, then C2 is written as A2 B2 plus, this is OR operation and this is XOR operation. So, A2 XOR with B2 into C1. So, now if I put this C1 over here, if I just in this particular equation, if I put C1 over here, so at that time what it will be? It will be A2 B2 plus A2 B2 into this A1 B1 plus A2 XOR B2 into A1 XOR B1 into C0. But what we are doing basically here, we from this, so how we can develop this? So, that means for each of the stages we know that for P0 and Z0, that is for 0th stage or for the LSB position, right. So, for P0 and Z0, for this propagation, that is A XOR with Bi, and for generation, that is A into Bi, right. Now, if I just write that for Z0 and for P0, okay. So, for generation, what is that? That is Ai into Bi. Okay. So, that means A0 into B0. For P0, that is A0 XOR with B0, right. Now, for C0, what I can write, that is Gi plus Pi into Ci. Okay. Sorry, this is Ci minus 1 if I write, and this is Ci. Okay. So, if I, that means from the beginning, now suppose I am having let us consider 4 bit. Okay. So, this is A0 B0. So, for this, this is A0 B0, this is A1 B1, this is A2 B2, this is A3 B3. Okay. So, for Z0 and P0 of this, what is that? That is G0 is A0 into B0, for P0 that is A0 XOR with B0, this is A0. Okay. And this is the carry in which is basically coming over here for this particular stage. Okay. So, then the carry, that will be what? This, if I consider this. Okay. So, then for this Ci is this for C1, that is A1 for this particular case, as for I am not considering this because this Ci minus 1 is 0. So, this will not be come over here. So, I can calculate this C1 from here. So, at the time what will it will be? Gi is nothing but this A and B
plus A1 XOR with B1 along with this Ci minus 1. Okay. So, that means which is nothing but this C1. C1 is this. Now, if I just C1 will be what? Ci1 will be again if I just put this as, so that is nothing but the Z0. Okay. So, Z0, that is Z0 is A0 B0. So, that means now what I can write, this is A1 B1 plus A1 XOR B1 along with A0 B0. Okay. If I in the same fashion, if I just want to calculate C2, so at that time what it will be? It will be like A2 B2, this G2 plus this will be A2 XOR B2 along with this C1, this is C0, this is C1. Okay. This is C0. So, C1. So, now C1 is what? C1 is nothing but this particular value. So, if I just put then A2 B2 plus A2 XOR B2 into A1 B1 plus A1 XOR B1 A0 B0, sorry not this, A0 B0 after that. So, that means here I have generated this C2 C1 from the very beginning. Why? How? By generating this Z0 and P0 term in each of this case. Okay. So, what we are doing? That means, for each of this stage we are generating, for A0 and B0 we are generating two cases, which is G0 and P0. For each of this case we are basically, for A1 and B1 we are generating G1 and P1. For each of these stages we have already generated the corresponding G2 and P2. Now, the carry over here at this particular stage, okay, for C1 I need, that will be Z0 plus P0 into C0. For C2 it will be G1 plus P1 into C1. So, P1 into C1 means again this will be replaced by, this will be replaced by Z0 plus P0 into C0. So, ultimately if I just put it like this, G1 plus this is P1 Z0 plus P1 P0 and C0. So, C2 will be something like this, it will be G2 plus this one. So, G2 plus this one means this G1, sorry, this will be G2 P1 plus G2 Z0 P1 plus, sorry, P2 and P1, then P1 P2 P1 P0 and C0, something like this it will be continued. Okay. So, in each of this case you see that it is having Z2, I have already from the beginning I have calculated that, then P2, P1 and P0 I have already calculated. So, now whenever I am just increasing these values, so at that time what I need? I need some of the AND gates for this and some of the, that means OR gate for this, because this particular operation from the beginning I have done. So, this C1 and C2, C3 that are available It is not that whenever I am computing this C2, I have to wait unless and until this C1 computation is over. It is not like that. I am computing each of these carry signal at a time simultaneously here. Okay. So, that means now the problem is there, that means whenever I am computing this C2, at that time the levels of this that is increasing. If I consider this more on of n, if I increase the number more, so at that time the levels of addition over here that will increase, but the thing is that I do not have to wait unless and until this is basically finished, which is happens in ripple carry adder. Okay. So, this is the, that means operations of here. If you just see that this is the 4-bit carry look ahead adder. So, here this AI BI and it produce this PI and GI, then again PI plus 1, GI plus 1, PI plus 2, GI plus 2, PI plus 3, GI plus 3. So, then CI plus 1, how it basically computes, that is GI plus PI into CY. Then CI plus 2, that has been computed using GI plus 1 plus PI plus, that means that is nothing but this. So, instead of I, that will be I plus 1, while CI is now this CI plus 1, that will come over here. So, something like this I will get of this expression. So, CI plus 4, that means CI plus 4, what will be the expression, that is GI plus 3, PI 3, GI 3. So, this is up to this is for the generation of the carry, and this particular P, what we have seen, that P2, P1, P0 into the last C0, this C0. So, that is the, this particular expression is for propagation of the carry. Okay. So, more that means if I consider is 16, so 16 number of this PI signal that will be considered over here. Okay. So, this is for carry look ahead adder. Okay. And so, here you see this 1 gate delay for calculating this GI plus 1 and PI plus 1. Why? Because XOR gate I require for this for generation of this, sorry, for propagation of this, for generation I need AND gate. So, that means 1 gate delay for these particular things, and for this P and G group 1D calculate P and 2 for calculating G. And for the final CI plus J, it needs 3 gate delays to calculate C4I J plus 1. Why? If you just go back to this. So, if you see, that means 1, 2, 3, 4, if I just consider this. So, at that time this will give me, that means what is the levels of gate I need for computation of this. Okay. So, this indicates that thing only. So, the total number of, that means gate delay is 1 here, 1 for calculate the that means 1D to calculate P and 2 for calculating the G group, and 3 gate delays to calculate C4 J plus 1. So, that means the total is required, that is 1 plus 2 that is 7, sorry 1 plus 1 2, then 4 plus 3 which is 7 gate. But in that means in carry look ahead adder, that will be 8 gate delay. Okay. So, that means I can reduce the corresponding levels for 4 bit only. If we consider more on of this at that time, I can get more the savings, but for 4 bit I can say I can save 1 gate delay in compared to ripple carry adder. Okay. So, this is the, that means 32 bit carry look ahead adder. Okay. So, we have grouped into 4 bit look ahead carry adder, and then this 4 bit whatever, that means the carry we are considering, then we have just subdivided into this corresponding to considering 4 of this is 16 bit adder and this is 16 bit adder, then these two finally basically added again, and we are getting the corresponding final C out. So, the total that means the delay will be any of this particular group. Okay. Either it may be comes from this to this to this, then that, or this to this to, because it has to pass through 1, 2, 3, 4, 5. Okay. So, 5 of this particular block. So, that is why the delay for this 32 bit carry look ahead adder will be something like this. So, this group is basically used for carry look ahead adders of 4 bit blocks generating this G I, G star I, P star I and C in for 4 bit blocks, and this is the, that means grouping final carry C out and C 16, and here carry look ahead adder, this 4 of this 4 bit generating for G I, P I and C in for the adders. So, the total critical path delay for this, 1 gate delay for computing G I and P I. So, that means for generation of the carry and propagation of the carry, 2 into 2 gate delay for again G and P, that means the computation of that we have already seen, and 3 into 2 gate delay for C in, and that means C in means the last one, and then for 1 XOR gate delay for some total approximately 12 gate delay we will get for this particular 32 bit carry look ahead adder. Okay. So, this is that means expression here, that means there is a mistake, which is this will be XOR operation. So, in this manner you can just express or you can just extend the corresponding C 1, then C 2, then C 3, then C 4 in this something like this. Okay. So, this carry look ahead adder that are used, or that is used in Motorola one, that means one in Motorola's particular circuit. So, at that time it says that this critical path as it follows different, that means these blocks. So, at that time it has different of this delay element. That means, for this G0 to for 4 bit of this PG block, the delay here that is 1.05. Okay. Whereas, the same thing whenever this PG block it passes through the PG block, so at that time it is 1.7 nanosecond at this particular point. Then again for P15 and G15 it is 2.0, then for 31 it is 2.35, for 47 this is 2.7, for 51 that is 3.7, ultimately for 63 the total time is 4.8 nanosecond, and this is the, that means corresponding architecture for this. So, the critical path is that, which one is the critical path? It starts from the Z0, then it is coming from this, that particular, that is 3 to 15, that means for this 4 group. Okay. Then again it is coming to this, then coming over here, passes through this, then again it is going through this particular block, and it is ended at this C63, which is basically producing the this C64, which is the final output. Okay. So, this is the critical path A, B, A, that means that to Z0 to Z30, Z15 G47 then C48, C60, C63 and then S63. Okay. That means which C63 is used for S63. So, that will be the final critical path or for this particular system. Okay. So, this chip is basically used in one of the Motorola's chip. Okay. So, this says as opposed to the ripple or carry skip adder, the critical path in carry loop adder travels in vertical direction rather than in horizontal, as it, that means in the what happens in the, that means ripple carry adder, the carry is basically follows from this particular side. Okay. So, that is the horizontal one, but here in case of this carry loop adder, it is in the vertical direction. That means, the how much level I need for computing the carry. Okay, for C1 I need to carry, that means consider this G and P, considering this. So, whenever I am increasing more on that, so at that time this levels of computing this carry, so that will be the most critical path. Okay. So, that is why here the this critical path basically varies in the vertical direction, not in the horizontal direction, okay, which happens in the case of carry loop adder. So, therefore, the delay of carry loop adder is not directly proportional to the size of the adder n, but to the number of levels used. So, given the groups and supergroups in carry loop adder resemble a tree structure, the delay of carry loop adder is thus proportional to log function of size n. So, that means, if I use 8 bit, so at that time the corresponding levels which I require, that is log 2 base n. So, that is 3. So, the log dependency makes carry loop adder one of the theoretical fastest structure for addition. However, it can be argued that the speed efficiency of carry loop adder has passed the point of diminishing return given the fan in and fan out dependency of the logic gates and inadequacy of the delay model based on counting number of gates in the critical path. In reality, carry loop adder is indeed achieving lesser speed than expected, especially when compared to some techniques that consume less hardware for the implementation. So, where it will take, that means what is the condition of fan in and fan out dependency, what are those, that we will see in the next class. That means, how this fan in and fan out dependency, theoretically I can get this the corresponding that that means the corresponding critical path should be log of n, okay. But in practical we do not get that. Why we do not get that? Because of this fan in and fan out dependency. What is that fan in fan out dependency? That we will see in the next class. Okay. So, thank you for today.